Welcome to lecture 10. So in today's lecture, we will learn how neural networks, basically when they meet graphs, what field we create. So this is an intersection. This lecture is an introduction to an intersection between two fields, which is, the first one is graph theory, and the second one is deep learning. So when both these basically meet, they create what we call geometric deep learning, okay? So let's start from the beginning. For those who know convolution neural networks, I will not cover the whole, all the basics, but I will give you flashes or like highlight the most important concepts that we will use today to introduce graph neural networks, GNNs, okay? So first, as you guys know this, even when we studied diffusion or when we wanted to do clustering, everything relies on the concept of neighborhood, who your neighbors are. So the first rule is, tell me who your neighbors are, I will tell you who you are. And this is, basically everywhere. It's like, in unsupervised learning, supervised learning. It's also, it's the foundation of convolutional neural networks. So convolutional neural networks, or CNNs, they are based on, they are rooted in three fundamental concepts, okay? So the first one is locality, or what we call also, it's the neighborhood. The second one is aggregation, how we integrate information from the local neighborhood. So you have neighbors, you take messages from your neighbors, you listen to each one of them, and then decide how to integrate all that information together to do something, okay? Now, the third one, which is basically the rule of composition. It's like a function of a function, and this is what makes convolutional neural networks deep and creates the field of basically what we call deep learning. It's based on the rule of composition. Now, just to remind you guys, how does convolutional neural networks work? So first, imagine we have an image. This is our image. These values represent the values of different pixels in the image, okay? So we can, this is not colored, but you can color it. So you can, it can be anything. It can be a landscape image. It can be an image of a person, okay? And then our goal is that, okay, let's say we want to classify this image. We want to classify it as into different categories. Like, let's say, for example, whether it's a person or an animal. So this is, our ultimate goal. It's a classification task. To do that, usually in typical machine learning, where we left off in the machine learning course, is usually we use handcrafted features. So if you have, for example, let's say, maybe I'll add a page or go back here. So let's say you have two pictures, like, well, this is not something, I'm not a professional, but let's say this is a picture of a cat. So what you do, you extract features. For example, you try to extract the size of the ears, or like the shape of the nose, etc. So this is what we call handcrafted features, okay? So you try to extract features that represent or encode or characterize this object or this shape, okay? Now, in deep learning, what we want to do is we want to avoid handcrafting features, because these are not naturally easy to extract. Imagine if we have a picture or an image with different attributes, it won't be very straightforward. So the idea is basically, instead of handcrafting, we want to learn, okay, the features, or we want to learn feature representations. So this is the main difference between typical machine learning and deep learning. Machine learning, we use handcrafted features. Deep learning, we learn the features, okay? Now, going back to our story, so we have a CNN. How do we learn the features? So the idea is that locality and aggregation, and then composition. That's how we learn these features. So let's, decompose or like go over these rules one by one. So for example, let's say I define a filter. This is my, like a 2D grid with different values. Paste, okay. And then by sliding this filter over this image, I can create another image from the original image. So this, basically the output here is a learned representation from the original input. So we have an input image. We have a box, or what we call a filter or a kernel, that has values inside that, box. And then we multiply or convolve this filter with each pixel in this image. So we slide it, multiply, so convolve basically. And then we get the output. For example, for this box, we get a value right there, okay? So in this example, what do we mean by learning? Learning here, it depends on what? It depends on this W, right? So if we change the values inside this box, like I put 1s, 2s, 3s, every time I change the values inside the W matrix, I will change the output image, which is the convolution of the image with the filter, okay? So the idea in deep learning is that, or convolution neural networks, is that I have a filter. What does the filter do? It actually looks at a local neighborhood in the image. So let's say this is a central pixel here, and then I will look at my closest neighbors. These are my closest neighbors, okay? So here we have a spatial neighborhood, right? We know that. So these guys are my closest neighbors, okay? And then I will have a filter that will allow me to spot the local neighborhood, but also to focus on the local neighborhood, but also it will teach me how to aggregate it via the multiplication, okay? So let's say aggregated means I'm taking all these, values, multiplying them by my filter, okay, weights, and then summing them up, okay? So it's an aggregation process, it's an integration process. So this is basically taking information from all these neighbors and producing a single value that represents this box in my new output image, okay? So now so you can see, guys, that this is, we have seen the locality, the aggregation, and then what we also have the composition rule. So in deep learning, the composition rule is that, let's say, in this example, for the sake of simplicity, we're using exactly the same filter. So we're using the same filter size, and we're in the same values. The rule of composition means that we are here, for example, convolving this image with this filter, getting an output image right there. Okay, so this is my filter. I slide it, I get an output image, and then I convolve it again with this filter. I get another output image, and this is the composition rule. Okay, so it's a function of a function, and this is how the networks gets deeper. And slowly we're mapping this original image into lower dimensional representations. And actually this is the learned feature representation, the output. Okay. So in this example, we see how convolutions work on images, and these are the three basic rules. Now, if we want to do this on graphs, we know that these properties, we can easily define them on images, but the key question here is how to generalize these three functions, how to define a neighborhood, how to aggregate from neighbors, how to do the composition rules on graphs. And to do that, first we need to think about graphs. What are the similarities and the differences between these two objects? So we know, for example, that an image, it has a structure, it has a spatial locality, like, spatial neighborhood, which means here, for example, if I slide this filter over this image, I know if I am, for example, located inside the flower, my neighbors might be inside, right? So there's the local neighborhood tells me a lot about the structure, the content of the image, right? But for a graph, we cannot do that. It's not possible because it's not structured. So basically, the images are also, or also if we have like text data, right? It can be considered as an array, and in both cases, these are structured data representations, and they live in a Euclidean space, okay? So also, I would say like the original deep learning methods, they were primarily designed to operate on images and on Euclidean objects, okay? So, for example, simple sequences and grids. On the other hand, if we look at graphs, so what do we have? Graph, first, like you can have a data set of graphs. The size of the dimension of the graph, the number of nodes might vary. So this is, you can have an arbitrary size. It might have a complex topology. So spatial locality here is not present, right? So we have topological locality. And then graphs are actually non-Euclidean objects, and I have covered this in the first lectures in this course. Now, also there is no fixed ordering of nodes, so we don't we know that, for example, in images we can have a pixel I that is neighboring to I plus 1, etc. So we do measure the values inside these pixels, but here we don't have an ordering. We cannot, for example, order from 0 to k, etc. So to read this, we don't have a coordinate system. Okay. So now, these are all big issues, right? So big differences between images and graphs, and still we want to learn how to do deep learning on graphs. So let's think about that more. Now, this is just an example of a deep learning network. So you can see that we have, for example, here we have different layers, 3 layers. And ultimately, what we want to learn how to, let's say, classify these images into different categories. Now, what we're learning different representations of each of facial images. So in the first layers, we're learning very simple, basic features, shallow features. And as we go deeper and deeper, okay, we will learn more high order or like more representative, more representative features of the original data set, okay? So this is, a typical CNN. Now, if we want, let's say we have a set of graphs, instead of having images here, let's say we have a set of graphs. So these are my set of graphs. And for the sake of simplicity, let's say that all these graphs have the same number of nodes. Okay? Now, before we go and try to come up with a new theory, the most naive approach is basically what? If you guys think about, trying to classify graphs, okay? How can we apply a typical CNN on graphs without the need, like, what can we consider the graph as, basically? If we look at it, we can represent it as what? Adjacency matrix, which can be considered as what? As an image, right? So that's the most naive approach. It's like if we have a graph G, we have its adjacency matrix, right? And then this is, let's say an n by n matrix. And then what I can do, like this adjacency matrix, it has values inside it. So I can look at these values as pixels. And then just, train on the set of adjacency matrices A1 till ATR, okay, for example, okay? So, yes, so what do you think about this approach?
It doesn't seem very intuitive to me because the ordering of the nodes can change.
Absolutely.
When you're convolving something else with it, the order of that can change, and the things that you're convolving together can vary.
Very good. So basically, what you're saying is that, well, this is very naive. Let's try it. Does it give us good results? Probably it will give you something random. By chance, it might give you something good, but this does not actually exploit the mere properties, the fundamental properties of a graph. And the problem is that with the adjacency matrix, if you change the order of nodes, everything changes. You have like 1, 2, 3, 4. You have 4, 3, 1, 2, okay? So your adjacency matrix changes, but actually your graph does not change, right? And if you convolve with a filter, all representations that you have learned will change, okay? If you just permute the nodes. So this is a problem. We don't want to do that. This is not a good solution. This is actually naive. That's why we called it naive. It's not a good solution for this. So alternatively, now there's another problem with that. If the graph has different sizes, right? So we cannot use a typical CNN. We need to resize the graph somehow. Resizing a graph, what does it mean? Okay, how do we resize a graph? So let's say we have a graph like this. It has 4 nodes, and then if all your input data is of size 2, it means you need to remove nodes and connections, and this is not good, right? So here, going back. So a hint to the solution is to think about how to define the following tools on graphs. How can we generalize locality, aggregation, composition, which is, stacking layers on graphs, and thereby we will be defining graph neural networks. Okay, so I'll give you guys 2 minutes, and I would like you to think about this, okay, and give me a few suggestions. So don't look at the review paper. Okay, well, it's okay, you can look. What I meant, I know some of you maybe are aware of the GNN theory, but try to think of, like, using the tools that we learned in this course about graphs, their properties, their topology, topological measures, all these things. How can we generalize or define new locality, aggregation, composition rules, or maybe simply try to generalize without without changing the basic operations that are defined in CNNs fundamentally. Okay? Any ideas? So how do we define a local neighborhood in a graph? So let's say we have a graph like this. So remember, when we do convolutions, we are looking at a single pixel, right, in the image. So for example, here, this convolution is like, it's centered at around, like basically this pixel, right? And then we're trying to somehow aggregate messages or information from the neighbors of this center pixel. How can we possibly generalize this to graphs? So let's say, for example, this is my node of interest. And then what we can do is that, look at what? It's neighbors, right? Very, very straightforward. So we can extract its neighbors, right? And then these neighbors, we find locality because they're local, right? And then what we can do, we need to learn how to somehow aggregate or map or transform information from these neighbors. Okay, so this is what we need to do, like aggregate. So aggregation is that how can I combine all of that? But before we aggregate, of course, we need to learn how to transform, because we have, if you guys remember, we had our W, like the weight. So we need to map or transform and then do the aggregation, okay, the combination of all those messages from local neighbors. Now, going back, how we do that. So let's define a graph. So let's say this is our input graph here. And then what we have the adjacency matrix of G, and X is a node feature matrix. So A is of size n by n is the number of nodes. X is of size m by n, where m basically is the number of features, and here we have n is the number of nodes, okay? And then what do you guys call this graph? Because it has features, which means for each node xi, I assign a feature vector, okay? Let's call it xi. There's a name for this graph. What do we call them? Decorated or annotated graphs, okay? So here in this lecture, we will focus on what's called decorated or annotated graphs, which means each node in the graph, it has a feature vector assigned to it. Okay, good. Now, in the next step, what we want, in this step, we will look at graph encoders. If you guys know autoencoders, how they work, you might have an idea about that, but let me explain it very simply. So our goal is to do node embedding, graph node embedding, or encoding. How do we do that? So here in this example, when we say GNNs, trying to learn graph representations, okay, we will not change the graph. So the graph structure in this lecture, just for the sake of simplicity, it will be unchanged, okay? However, we have feature vectors assigned to each node in the graph, and our goal is to learn an embedding of the graph itself via these feature representations, okay? So let's say, for example, we defined our graph G, and then this graph, these nodes can represent what? It can be anything. So for example, if you're classifying objects or images, let's say, you know, you want to know if this is a tree or something else, like let's say, I don't know, this is not a good example, a tree, or let me put my cat back, or a cat, okay? So you want to classify those. So you extract features, you represent those by your feature vector, right? And then what we want to do, we want to classify actually, you know that there is a problem of high dimensionality. We have seen this. So typically you can use, for example, PCA, principal component analysis, to embed, to reduce the dimensionality of your samples. Okay, so ultimately what we want to learn, we want to go from a high dimensional space of dimension m, okay, which means each node has m features, to an embedding space of dimension d, where d is much smaller than m, okay? And we hope that any task that we do in this space, for example, classify or cluster, we will have a better representation of the data, because we learned how to embed it in a low dimensional space that is most representative and computationally less expensive, okay? Most representative of the data. Now, what is the key idea here? Why we're using graphs in the first place? We could just, you know, train, for example, a typical SVM, support vector machine model, and then classify these objects. We can also do dimensionality reduction, like using feature selection, and then try to classify them. But the key idea about encoding your samples in a graph is that the graph enables us to capture the similarity between these objects, okay? So how we define the similarity is very important. Let's say if two objects are very similar, okay, like for example here, if two objects are very similar, like U and V, they will be neighbors or very close to each other, okay, if two samples. Now, our goal is to try to learn an encoding function, let's call it, or a mapping function, encode, which maps each node V in my graph into a ZV in the embedding space. So let's see how we can do this. In this example, we take this node, okay? and then we will learn the embedding. And via this embedding, we will have our new node here and a new representation of its features, right, of size what? D. So this is actually our ZV here. But the key idea is that when we want to do the encoding of a graph, what makes a difference between other methods is that we want to preserve proximity. What does it mean, preserve proximity? It means that if two nodes are close to each other, are neighbors in my graph, I want their encoded, or I want their embeddings to be very proximal, to be close to, okay? So Z, if I do it in the other direction, it can be in the other direction, but it's fine. Okay, so maybe I do something like that. So this is my ZU and the embedding of this node, okay, the projection of the features onto this space. So this is the key idea. The key idea is that the similarity between two nodes U and V, if these nodes are very close in the original space, I want the dot product of their embeddings to be also, to have almost the same similarity or distance, okay? So that's what it means. So this is, you know, the new representation, ZV and ZU. And here, remember, so what we have here, we have actually the XU and we have the XV. These are the feature vectors, and now we have their corresponding embeddings of low dimensionality, and this is the encoding function. Okay, so this is what we want to do. How are we going to solve that? We will learn about this in a minute. So basically, let's recap and formalize this mathematically properly. So what we have a similarity metric that we need to define, and now you guys know that we can define similarities in different ways, right? We can smooth them, we can diffuse them, we can merge different graphs together through cross diffusion. We can use a predefined metric, like for example exponential function, Gaussian kernel. So because the similarity is very important. Why the similarity is important? Because you predefine, you preset the relationship between all these samples. If your similarity is bad, you might have a tree neighboring, for example, a completely different object, okay? So the similarity is very important. Now, once you say, okay, I have a good similarity measure, I trust my similarity measure, then I want to learn an embedding which preserves this similarity measure, okay, between my samples in the embedding space. And this is what we're doing. So we're mapping relation. So this is actually maps the relationships in the original graph to relationships in the embedding space, okay? And what we want to define is these two. So we want to define first the similarity measure, and second, the encoding function. How are we going to define the encoding function? Okay, so we already have some from the previous lectures. We know how to define a similarity matrix between samples to build a graph. So an encoder basically here, it maps a node feature vector to a low dimensional space. So here we have the node in the input graph, and we have its embedding in the d-dimensional space. So ultimately, what we want to learn is this embedding. So we want to learn a Z matrix, or what we call the embedding matrix, where the embedding of, where basically the number of rows, they represent the size or dimensionality of the embeddings, okay? And then the number of columns, we have basically the nodes. Now, to do that, we need to define our encoding function. And this is where all the properties of GNNs or deep learning comes in. So we need to, when we define the encoding function, we need to preserve locality, think about how we're going to aggregate and how we're going to make this the learning of these embeddings deep via composition, the composition rule. Okay, so the idea is that for the encoding function, this is what we are interested in. Okay. We can define it as multiple layers of nonlinear transformations of the graph structure. And this is very similar to how encoders work on images. But let's look at how we're defining this on graphs. So here, one rule, we need to find your neighbors and define your aggregation rule to propagate information across the graph node for node feature computation or embedding learning. So what does it mean? For example, here, if we have an image and we want to convolve it by a kernel, the weight matrix here, we will get ultimately, by convolving this box with this kernel, we get this value, right? So what we did ultimately is a summation of hi. These are the values inside my, like coming from my neighbors, okay? So this is an hi, and this is the wi, that is my weight matrix that I need to learn. And then I just simply sum up transformed or mapped neighboring messages hi by wi, which means wi here is my mapping function, okay? And this is how CNN works. However, for graphs, what we can do, we can look at the local neighbors, and here we have different, you know, neighbors to this, to the red node, and then we think about how we're going to aggregate them. Okay, now let's define this. So a basic approach is basically to average messages from neighbors. So we can just, as an aggregation function, we can simply take the average, which is very simple, okay? And then the second step is to apply neural networks. So we first average messages from neighbors and then apply neural networks. So let me explain this step by step. It's not very difficult, actually. It's very simple. So here we have an input graph. This is our input graph, and this is the target node. So we will try to learn what? The embedding ZA, okay, of node A. So it means like this node has a first feature vector. Let's call it XA, for example, okay? And we want to learn the embedding of XA. How we do that? We first have the, forget about the layers, let's just look at this. We need to look at the whole thing. So basically, the first thing is we try to find the immediate neighbors of node A. What are the immediate neighbors of node A? Guys? Yes, B, C, and D, okay? So we retrieve the neighbors, B, C, and D. And then for each neighbor, we also find its neighbors. Okay, so very simple. Then for node B, I try to find, I identify its neighbors. So choose another color, for example, this one. So the neighbors of node B are C and A, okay? So I put here C and A, like A and C. So you guys can see, so basically these are also the neighbors of node C. This is the neighbor of node D, etc. So this is, you know, a neighbor of a neighbor. And this is how we create, basically, important thing, this is how we create depth in graph neural networks. So we say you go one, so these are rings of neighborhoods. So one step, and then you also look at the local neighbors of these nodes, etc. So a neighbor of a neighbor. And you can see there's composition here too. Okay, now what do we do here? It's very simple. Let's look at this. So we have the original features. These are the input features of my graph, okay? And then this is what we call the first layer. Then we need to identify, we need to define an aggregation method. So we aggregate these, the representations of these two nodes, okay? What we have, the features of these two nodes. Then we perform we apply a deep learning mapping function. So this is the neural network. It's inside this box, okay? And then we do this for all other nodes. So we aggregate messages or features stored in each of those nodes, and then we apply our neural net or transforming, nonlinear transforming or mapping function, and then we do this at the first layer. Then if we want to move at the next layer, we do the same thing. Now, after the output of a neural net is a mapped feature vector, and then what we do, we pass it on to this node, okay? So we pass everything on to this node, and then we map again. So this is actually the feature vector that will be stored here, outputted by this neural network, okay? And then we aggregate them again. After the aggregation, what we do, we map using a deep learning model, okay? And then the output of the deep learning model will be our ZA, the final embedding. Okay, you guys get the idea? It's very simple. This is, this is the foundation of, graph neural networks. Now, how do we do that? Let's formalize it now mathematically. So here we have our graph. We want to learn the embedding of each node in the graph, but in this case, we have only focused on node A. But of course, we need to generalize this. We need to investigate or operate on each node in the graph, okay? So in this example, first thing, there are 3 steps. So the first step is we set our initial embedding at the 0 layer. Let's call our embeddings a vector H, and this is the embedding of node V, okay? And we set it to the node features. So this is, the feature vector assigned to my node V. Now, in the next step, what we do, we learn, this is the aggregation and the deep learning. So this is, we estimate basically for the same node, okay, for the same node. First, we have HV, let's call it here, for example, we have HA level 0. Then we go, for example, to HA level K. How do we estimate this? So let's look at this equation here. First, inside, we do the aggregation. So we average the neighbor's previous layer's embeddings. Okay, so we look at the each neighbor U belonging, each node U in the vicinity of node V. Okay, so these are the immediate neighbors. If you guys go back, these are the immediate neighbors right here. Okay, and then what we do, we sum them up, sum their embeddings in the previous layer, okay, and divide by the number of nodes. This is to normalize. So this is simply aggregating. It's very simple. So let's say here, these guys, if I do this, we write them down properly. So this is layer 1. So this is HB layer 1, HC1, HD1. So I just sum these guys, okay, and divide by 3. It's very simple, and that's how I get the aggregated the aggregation of messages from different neighbors. Next, what we do, we need to multiply by the mapping function W. So what is W? Actually, this is the matrix, the weight matrix that we want to learn. Okay. So here, what we have inside this box is actually the W, but we also have the B. So these are the parameters of my deep learning model, and these are very typically, optimized in GNNs. Okay. So once we do that, so once we aggregate, we map. So this multiplication actually allows us to map or transform the messages that I'm getting from all my neighbors, okay, for a node V. So you need to understand the intuition. And then what we're doing, we're adding a bias. So this bias is very important. So we're looking at, the current node V, the target node, and it's embedding in the previous layer, okay, and adding some bias because we might have some noise. So this accounts for some noise or for variation in the data set. So we add a bias. And after that, what we get this whole basically transform data from the neighbor and also from the neighbors of the current node V and from the node itself. And then we do, so all of this up to this point is what? It is linear transformation. We agree on that. So all of this is linear. Now, when we apply the sigmoid function, this is what makes it nonlinear. For example, we can apply the ReLU, and here we get the embedding. Okay, so here WB, and we have our sigmoid, and this is, you know, nonlinear transformation of the previous embedding, okay? So great, so this is actually it, and then we iterate many times. So let's say we have k layers, so this is the depth. What is the layer here? It means we're exploring how many compositions of neighborhoods, k, okay, a neighborhood of a neighborhood of a neighborhood. You guys need to keep that in mind. So these are the number of layers, and then ultimately we will find the embedding for our node v, okay, after k layers of neighborhood aggregation, and this is the final one. Okay, so you guys get this, and then after that, this is good. We can do so many things with this theory. There is a whole lot to improve, right? But this is the foundation of GNNs, average messages from neighbors, apply neural network, and we get our GNN. Now, one thing is that, okay, if you look into the boxes, yes?
Can we continue doing this until infinity?
Not infinity. Yes, we can theoretically, because but you're gonna revisit the same neighborhood over and over again, right? Because the graph is self-contained. If you do this multiple times, you'll see at some point your loss function will either, you know, it will increase, it will not be good. So you need to train your model at a specific depth. So you can try different depths and then see how the performance changes with the depth. Okay, so that's one way of learning how to fix the depth of your model. Okay, yes?
And for graphs where I just connect only two nodes, for example, only two layers are meaningful, or can more layers be meaningful?
So this is a very good question. So is one layer is meaningful or two layers? It depends, I guess, on the complexity of your graph, on the topology of your graph. And generally, this is what we call, this is the shallow model, right? So shallow models in the literature, here, if you just use it, it will not give you a lot of results because, I mean, very, very impressive results. You might get good performance, but if you go slightly deeper, you might boost the, for example, if you're classifying nodes in a graph as you know, like into two classes, for example, let's say if it's a brain, healthy brain, or you know, disordered brain, then what you need to do, you need to slightly go deeper to investigate more how the furthest away neighbors influence the current node. But this is a trade-off. There is a lot of research on this topic. How deep can you go, right? Also, you know, like there's a trade-off between the computational time, because the deeper your network, the more resources you need to train it. Okay, so maybe if you have a classification at 80% with only two layers, that's okay for you. Okay, you don't, if you use maybe 5 layers, you get a boost of 2%, and for your application, at 2% is not very meaningful. So it depends on the data, on the application, and this is a very good question. It's an active area of research. Now, how can we prove? Can we demonstrate or mathematically prove or estimate the number of layers? This is something that's ongoing, basically. It's still under investigation, how to automatically look at this. And if you are curious, there's a very nice paper. It's called GNN. I forgot in which year it was published, but a few years ago. And then it's called Genetic CNN. And in this paper, what they're trying to do, they're trying to automatically learn the architecture of CNNs, okay? So how to learn, what does it mean learn the architecture? How many filters, how many layers, and all these parameters, they're training a genetic algorithm to learn how to automatically design the optimal architecture for your task. It's a very nice paper. So that's basically investigates this point that you just raised. Okay.
Sorry.
Yes?
Is the dimension reduced? The operation, I don't see the dimension reduction here.
Right.
The dimension of the x.
Oh, it's the W. Because of the W. The W will reduce the dimension. This multiplication, this is, you know, will lead to reducing the dimension step by step. Yeah. Yes?
What if our graph is fragmented?
Very good question. What is our graph? What if our graph is fragmented? Right. So if you have fragmented graphs, it means that in that case your neighbors are far away. So the similarity here, it will be set to 0. I think if you have a similarity, it might, I don't have an immediate answer to your question, but just thinking about it. So if you put a 0 in your matrix, right, and it's in your graph matrix, that's fine. The adjacency matrix of your graph will not have infinity numbers, okay? So if you have a node right here, the similarity between these two nodes, and they're disconnected, right? We agree on that. So it will be 0 because we're operating using similarities, not distances or dissimilarities. So you will not have the problem of infinity in your matrix. So I don't think it's going to change a whole lot. Like you can try it, yeah, for fragmented graphs. Good question. Okay. Now, how to, basically, we know now that we have, we want to estimate this, but ultimately to estimate the embeddings for each node, we need to train weight matrices. So this is actually what we learned, the W and the B. And here, to do that, how to train such a model, we need to define a loss function. And if you guys have taken a machine learning course, you already know this. So it depends if you want to do supervised learning or unsupervised learning. You need to define a loss function, and that loss function will allow you to estimate your W and your B, and that's basically how you will get your embeddings, okay? So here, there is another formalization of exactly the same, these three steps, so we can rewrite them in the matrix form. And to our surprise, maybe not to our surprise, what we see emerging if we do this, so we have basically embeddings. These are the embeddings that we want to estimate for all nodes at the nth layer. And we will feed these embeddings to any loss function and run stochastic gradient descent or a gradient descent algorithm, okay, to learn the aggregation weight matrices, W. So here W0 replaces the B, and this is actually the W1. And what we're doing, we notice that in this example, the A tilde is actually the normalized symmetric graph Laplacian. Why is that? Because it encodes actually the structure of the graph. Okay, so through this update, by solving this, we can easily get the embeddings of all nodes at the L+1 layer in this case. And these guys here, so the blue one, this term, it is based on what we call a self. This is the bias and the previous embeddings of this node and the embeddings of this node in the nth layer, the previous layer. And for this term, the other term considers all messages coming from neighboring nodes, okay, for this one. So this looks at the neighbors, and this looks at the current node, for example, at the current node here, the blue one, okay? Now, GNN model, just to summarize, so what we have, first, what we need to do, these are the design steps. We need to define a neighborhood aggregation function. So in this example, what did we take? Average, right? And then define a loss on the embeddings. It depends on if you want to solve a supervised or unsupervised task. So this is basic machine learning. Then train a set of nodes or a batch of compute subgraphs. So I'll explain this now. And then we can generate embeddings for the node. So how do we do the training? So in this case, we do a node-wise training. So node by node. So we feed, subgraphs to our model. And every time we try to optimize the loss function for node A, node B, node C, etc., iteratively in a batch manner. Okay. So this is what is done here. So we have what we call a compute subgraph for node C. So we extract its neighbors and the neighbors of its neighbors. And then we estimate these small deep learning models, the the weights, the W and the B matrix, and we do the same for node B and node A. Okay, so these are our compute subgraphs, but what do you guys notice? So our model will be trained using those, but if these are trained completely independently, it's a big problem. Why is that? Because we will learn a WC and a BC for each node. This will be very time consuming and computationally expensive. So BB, for example, and we have WA, this is the bias, BA, okay? So to solve this problem, what we can do is that sharing the parameters across all these samples, okay, subsamples. So we learn the same mapping functions WK and BK at the kth layer across all nodes, and this is, this sharing is done in in training of many conventional deep learning convolutional neural networks, okay, the sharing. Okay, now before we wrap up, so for example, let's say we trained our model on a graph G, so this is our input graph, okay, and then we want to generalize it to a new one, so that's not very difficult, even if we add because we performed a node-based representation, so we can just apply the encoding function and we can easily get the ZU for any new graph because it's based on locality, local neighborhood, so it's very adaptable to lots of structures. For example, we can train a protein interaction graph from a model organism A and generate embeddings on newly connected data about organism B. Okay, so it's very generalizable. And just to recap or sum up, so we have, for example, this is our training graph, and let's say a new node arrives, so easily we can get its local neighbors, okay? And then what we do, we can generate the embedding on the fly just immediately because it's all based on the local neighborhood. And okay, just to recap what we have seen, so first, GNNs, they are based on locality, aggregation, and composition. Composition is a neighborhood of a neighborhood. This is the depth of our network. And then these are the three basically rules that we use. So this is the aggregation. This is these are the learned weights. So here how we're aggregate using the learned weights. Then the nonlinear mapping, including the bias. So this is the deep learning network. And if we iterate many times, that's the depth that we're getting. Okay, we're getting different layers. And yes, so basically that's it. Now, before we wrap up, I have a question. Now, if we're in the aggregation rule, let's say up to this point, we use averaging. Okay, averaging means I look at all my neighbors, I take their embeddings in the previous layer. So let's say I want to estimate H of my, this is node U at layer K, okay? So I look at all these nodes, V1 layer K minus 1, H V2 K minus 1, etc. These are the embeddings of the neighboring nodes at the previous layer, and I sum them up, okay? So I just create the average, simply. Now, what's the problem with that? Let's say, for example, you build your graph. These connectivities, these edges and their weights, they depend on what? Remember, they depend on the similarity that I have defined to build this graph in the first place, right? Now imagine that my similarity measure or metric is not very robust to noise or outliers, okay? So I might maybe have connected this neighbor, like right here, this sample, to my current node, but these two samples are actually not similar, okay? So in that case, what can we do? We can pay attention, for example, to the neighbors that I trust most, that are most similar to me, maybe the closest ones. And this is what we call also attention mechanism in deep learning. And there are many other approaches and variants of these models. All you need to think about, guys, is this. What are the pros and cons of the method that I'm using to define locality, to define aggregation or composition? maybe they are good, but also maybe they are bad, or maybe they're not as reliable, or maybe I can do better. How can I improve each of those steps? And by thinking and contemplating over these questions, you can create better GNNs. Okay? Great. So, right. So what we have, we're going to look at in a bit. So we'll have a look, have a read at this paper, Comprehensive Survey on Graph Neural Networks by Wu and co-authors. So this is a new research paper, like review paper. And I really like how they cover different concepts of different architectures. And there are like nice summaries with many tables. So these are different architectures of graph convolutional neural nets, and what are the inputs, if they use feature matrices or not. So yeah, great. So any questions?